Welcome to the Comparison of Means, the T-Test, Video 1, by Elizabeth A. Albright at the Nicholas School of the Environment. So the steps to a T-Test. The first thing you'll do is set up a question of interest. Typically with a T-Test, we are looking for difference in means. And that difference of means is developed on a continuous or numeric variable. And that variable can be a one sample or one group, or two independent samples or two groups, or paired samples, such as a pre and post test type question. The next thing I always do is visualize the data. If you have the original data, always good to look at the distributions, and we will talk about assumptions in the next video. And based on the visualizations of the data, we need to examine whether the assumptions of the t-test are met and whether the t-test is an appropriate test to run, given the data that we have and the assumptions that we make about the populations. So once we are set and decide on a t-test, whether that's a one sample, two independent sample, or paired sample test, we need to set up null and alternative hypotheses. We also need to decide if it's a one-sided or two-sided test, and we illustrate this in our hypotheses. From there, we calculate the appropriate t-statistic, and that will differ depending on if it's a one sample, two independent sample, or paired sample test. From the t-statistic, we will determine the p-value based on the t-distribution, given the appropriate degrees of freedom. And based on the p-value, we will interpret the results in the context of the question and the hypotheses, the null and alternative hypotheses that we established. So here's an example we will work through today. Auto exhaust and lead blood concentrations. Researchers took a random sample of taxi drivers from Rome, Italy, and measured the level of lead concentration in their blood. We want to know if taxi drivers in Rome have higher concentrations than 50 micrograms per deciliter. A random sample of 150 taxi drivers who experienced constant inhalation of automobile exhaust fumes in central Rome had an average lead blood level concentration of 50.5 micrograms per deciliter and a standard deviation of 15.0 micrograms per deciliter. So please feel free to stop the video now and write down what the problem presents. In particular, I'd like you to think about whether or not a one sample test, a two sample test, or a paired test makes sense in this context. Will we use a Z or a T test, and why? Should we use a one-sided or a two-sided test, and why? And then I would like you to develop the hypotheses, the null and alternative hypotheses. So please go ahead, rewind the video to the previous slide, and answer these questions. One sample, two sample, or paired, Z or T, one-sided or two-sided, and develop the hypotheses, the null and the alternative. Once you've done that, please continue on with the video. Great, welcome back. So let's see how you did. Which test should we use? So the first thing I always think about is this one sample test, two sample test, or paired test. In this case, this is a one sample test because we are comparing one sample of blood samples of 150 taxi drivers in Rome, and comparing that mean to a population mean, or some null value of population or given value, and that's the 50 micrograms per deciliter. So we're going to use a one sample test. What would a two-sample test look like? That would be if we were to compare blood lead levels of taxi drivers in Rome to, say, Paris, right? Two independent samples. A paired test would be looking at blood levels of the same taxi drivers before and after, say, some intervention, so the adoption of some air quality policy. And then we would measure blood lead levels before and after the policy to see the difference. But in this case, we're looking at a one sample t-test. The next thing we think about is whether it is a z or a t-test. And we're going to use a t-test here because we don't know the standard deviation of the population. All right, we are making an estimate of the standard deviation of the population from the standard deviation of the sample, or S. So we know S, we don't know sigma. So we will use the t-test. Sigma is the standard deviation of the population. So should we use a one-sided or two-sided test? In this case, we're going to use a one-sided test because we want to know if lead levels are greater than 50 micrograms per deciliter. So there's directionality there. It's not a equals not equals test. Right? It's a lesser or greater. In this case, it's greater. And then finally, we need to develop our null and alternative hypotheses. So the null in this case will be the population mean, and we always talk in our hypotheses about the population, not the sample. The population mean of blood lead levels in Rome is less than or equal to 50 micrograms per deciliter. And the alternative is population mean blood lead levels in Rome greater than 50 micrograms per deciliter. You can think of the alternative as what we're trying to see if there's evidence in support of. Right? And we're interested in, or our central question is, are blood lead levels in Rome greater than 50 micrograms per deciliter? Is that mean greater than 50 micrograms per deciliter? So, one sample test, we need to use the appropriate test statistic. And in this case, it's T equals X bar minus mu naught all over S divided by the square root of n. And we know that the degrees of freedom is n minus 1. That means if we know the mean and we know n minus 1, we could solve for that last observation. So we have 1 less than n for our degrees of freedom. So again, the test statistic is T equals X bar minus mu naught over what we can call the standard error, which is the sample standard deviation divided by the square root of n. So to do this, we need to calculate the sample mean, calculate the standard deviation if we are using a t-test, which we are, calculate the standard error, calculate the test statistic, determine the p-value from the test statistic using the appropriate t-distribution based on the degrees of freedom, and interpret the p-value in terms of the hypotheses established prior to the test. So I will show the problem again in the next slide, and what I would like you to do is calculate out the t and the p-value from the test statistic as well as the degrees of freedom and make a conclusion in terms of the hypotheses that we proposed on the previous slide. So here is our t-statistic calculation. We have 50.5, which is X bar minus mu naught, the population value to which we are comparing it, divided by 15, the standard deviation of the sample, divided by the square root of 150, or the sample size. And we get a t-statistic of 0.41. So what does that mean? First, let's think back to our hypotheses. Remember, our alternative is that the population mean blood level in Rome greater than 50 is our alternative hypothesis, and it's less than or equal to 50 micrograms per deciliter for our null. And so we need to calculate the p-value of the probability that t is greater than 0.41 on a t distribution with 149 degrees of freedom. That is 150 minus 1. So here we have the t distribution of 149 degrees of freedom, and you can see that the area shaded in orange or to the right of 0.41, that's the probability of getting a t greater than 0.41 with 149 degrees of freedom, and that area is 0.34. So our p-value is 0.34. We could also calculate that in R. You could look at a t-table, we could calculate it in R. The R code is PT parentheses 0.41, or the t-value, the t-statistic, comma, degrees of freedom, and then I'm saying we want the upper tail, and so we set the lower dot tail equals to false. I call the object, which I named p dot value, and you get 0.34. So what does that all mean? What is this thing called a p-value? It is a conditional probability conditioned on the truth of the null hypothesis, right? So if the null is true, if the population mean blood lead levels is less than or equal to 50 micrograms per deciliter, we would expect getting the results we got are results more extreme, that t-statistic of 0.41 or more extreme to the right of that, or to the more positive, is equal to 0.34. It is a conditional probability, right? If the null is true, it's a probability of getting the test statistic we got or more one extreme. And so the smaller the p-value, the stronger the evidence against the null, right? It's critical to remember that the p-value is a conditional probability conditioned on the truth of the null. It is not the probability that the null hypothesis is true. So what frequent statistics often do is set a type 1 error rate, and we'll talk about that when we get to power analysis. We set that value kind of a priori and use that to judge the p-value. Often we set that at 0.05 or 0.01, and if our p-value is smaller than those levels, we go ahead and reject the null. Another kind of philosophy or approach to p-values is to think of it in terms of evidence against the null. And so the smaller the p-value, the stronger the evidence against the null. And so convincing evidence, for example, could be a p-value between 0 and 0.01. Moderate evidence between 0.01 and 0.05. Suggestive evidence between 0.05 and 0.1. So what I would expect in a report is report your t-statistic that was calculated, your degrees of freedom, the p-value, the difference in means. In this case, you would report the sample mean, 50.5, the standard deviation of the sample, and then make a conclusion in the comments. So to conclude, with a test statistic of 0.41 with 149 degrees of freedom, we estimate the p-value to be roughly 0.34. This is the probability that t is greater than 0.41 with 149 degrees of freedom. With a p-value of 0.34, we do not have strong evidence against the null hypothesis. We cannot conclude that the average blood lead levels of all taxi drivers in Rome, Italy is greater than 50 micrograms per deciliter. So in order for these results to be valid, we need to make some assumptions that underlie the t-test. First one is normally distributed population of blood lead levels. Again, we make assumptions about the populations, and here we're assuming that the populations are normally distributed, the population. This assumption becomes less critical as sample size increases, and we'll talk more about this when we get to the assumption section. Second assumption is independent observations. right? We do not want the blood lead levels of the taxi drivers to be autocorrelated or related to each other. And we're hopefully that we've fought against this through a random sampling process. So again, we have a p-value of 0.34. We do not have strong evidence against the null. We cannot conclude that the average blood lead levels of all taxi drivers in Rome, Italy is greater than 50 micrograms per deciliter. Thank you again for joining in the comparison of means, the t-test, video 1. This was written and produced by Elizabeth A. Albright of the Nicholas School of the Environment. Thank you very much, and stay tuned on the YouTube channel. All the best.